Last time we discussed the ideal oscillator, and now we shall discuss the damped oscillator. So, damped oscillator. Before I start the discussion, let us remember the most important results of the ideal oscillator. Sorry, remember. If the oscillator is ideal, its energy is E0. It's fixed constant. And the average energy or the potential energy equals the kinetic energy, that's E0 over 2. And we also used a phasor technique, which was not really needed for the ideal oscillator because the problem is simple, but to warm up to its usage in this problem and in the next one, which is the forced oscillator. So remember, we used in the ideal oscillator 0 e to the I omega 0 t, and this was a complex constant. Okay, and complex constant is like an arrow in the complex plane x0. This is its magnitude, and this is its angle. And when you multiply a complex number with another thing, you scale the magnitude, and the magnitude of this thing is 1, so the magnitude does not change. But you add the angles, so on top of psi, you add this omega 0 t, which makes it rotate. So why are we using it? Because this motion, this uniform motion around the circle with uniform speed is much easier than this motion, the projected motion along the line, which is the physical solution, but which involves the trigonometric functions, sines and cosines. So because this is so much simpler that we prefer to use it, especially in the case of the damped oscillator and the forced oscillator. All right. Now let's start with the damped oscillator. So let me just draw a picture. Here is a mass m. This is, however, moving, let's say, in a tube or something, which applies a friction. But of course, you can have different types of frictions, but an important class of frictions that appear in physical problems is proportional to velocity. And because it's friction, of course, it must oppose the velocity. So the equation of motion, m times a, remember dot means the same thing as d by dt, and this is a shortened, so double dot means second derivative. That's equal to, well, we have the restoring force minus kx. So far, it's the ideal oscillator. Now we add the friction force, and we parameterize the force and beta x dot, and it will come with a minus sign because it will be minus x dot, or perhaps I should write it like this, beta minus x dot. Namely, it is opposing the direction of motion. So this is the equation, which, however, will let me write like this: m x dot plus kx plus n beta x dot is equal to 0, or still, let me leave it here, equals minus m beta x dot. Now let me multiply with x dot this whole equation and arrange. This is d by dt 1/2 m x dot square, because when you take the time derivative, this gives 2 x dot, x double dot, and that 2 cancels that 2. Then plus 1/2 kx square, that's equal to minus m beta x dot square. Now, m is positive, beta is positive, x dot velocity square is positive, but we have a minus sign here. And if x dot is not 0, this is definitely negative. But these are functions of time, x dot, they are functions of time. Momentarily, instantaneously, it can be 0. So at that moment, instantaneously, it can be 0. But it is, most of the time, it is negative. The thing is that it is never positive. So you recognize this is the kinetic energy plus the potential energy. So altogether, it's the energy of the oscillator. So we can write dE dt is, it can be 0 whenever velocity is 0 instantaneously, but normally it's all negative. Namely, here we have an oscillator that is losing energy. Okay, so we shall study the motion of this oscillator. Erasing this. I am writing this equation here again because I will need dot plus kx plus m beta x dot is equal to 0, or we divide by m and write this thing as again x dot plus omega 0 square x plus beta x dot is equal to 0, and this is our equation that we shall work on. I'm erasing all these. Now, the solution of this equation. There are 3 cases. Let me write them. One is the underdamped, by which we mean still oscillatory. Since the energy of the oscillator is intimately connected with the size of its amplitude. If it's losing energy, that means amplitude of oscillations getting smaller and smaller. Or critical damping, or overdamping. Overdamping means that this is big enough so that it dominates the dynamics, and you have no oscillation. And here it is damped oscillatory, and this is just a transition from damped oscillatory to overdamping. I will not do the mathematics here, but I will give the mathematics as a homework. You can find it just if you scroll down the video, you will find you can click and get to the homework and study all these 3 cases. And for different physical problems, you want your oscillator overdamped or underdamped. But for physics, it's mostly this underdamped oscillatory. So I will simply write the solution, and we will, from now on, work with that solution. Okay? So the mathematics you can find in the homework, and you are led step by step to the solution. So, we will study not only the underdamped oscillatory case, but we shall also study, although it is damped, it is still a good oscillator. But if you wait enough, it's losing energy. So we are studying now damped oscillator, but which is still a sort of a good oscillator. Okay? So this is the limit we shall study. So we are looking at the oscillatory solution. Because most vibrating systems still vibrate even though they are under some friction. Okay, the solution reads like this. X equals notice that I am putting here another frequency, and omega prime square is given like this, omega 0 square minus beta square over 4. And we shall mostly work in this limit, that omega prime is like omega 0, and they are both much larger than beta. Okay? So, for example, this means that before it changes appreciably, this exponential decay factor, this thing still oscillates many times. So in that sense, it is a good oscillator which is damped. Okay? So let us look at the initial conditions which determine A and B. Now, of course, it's not as simple as or short as the ideal case, because we have another time-dependent function here. Okay? So let's look at x of t equals 0, which is x0. This is 1. This is a. Cosine is 1, a. And sine term is 0. The next term is v at time t equals 0, which we call v0. It is minus beta over 2 times a. I take the derivative, beta over 2. Then I put time equals 0. So sine term goes away. This is 1. I have a. Next, take the derivative of this one and set time equals 0. If you take the derivative of cosine, it is sine. Then it is 0 at time equals 0. And this gives me plus omega prime b cosine omega prime t, which is 1. So we have solved A and B. A is x0. B is 1 over omega prime. V0 plus beta over 2 times x0. So let us write the solution here. So this is the solution. Okay. Now we know that the energy of the oscillator is decreasing. Let us see how it decreases for a good oscillator. So I'm erasing this part. For a good oscillator, I am trying to write the energy E. For a good oscillator, X is like e to the minus beta t over 2, x0 cosine omega prime t. Here I have beta over omega prime, which I will neglect, plus 1 over omega prime v0 sine omega prime t. And I will take the velocity, which is dx dt. Again, let's make an approximate computation. There are two terms that depend on time, this exponential and that. If I take the time derivative of this, beta will come down and multiply this. And if I take the time derivative of that, omega prime will come out, and it will be multiplying the derivative of this, the sine and the cosine. So since omega prime is much larger than, let's write it again, omega prime is like omega 0, they are both larger than beta. I am looking at the energy in that limit, because otherwise it's too messy. Although we know exactly that the energy goes down. So we take the derivative now, e minus beta t over 2. I am only taking the derivative of this one, minus omega prime x0 sine omega prime t, plus omega prime cancels that, v0 cosine omega prime t. Let's check that at time equals 0, we have v0. This goes away. This is 1, v0, this is 1, okay. So that's the x and v. Let us now calculate 1/2 k x squared, which is the potential energy. So it is 1/2 k times x squared. We have e to the minus beta t. I will write s for sine omega prime t, c for cosine omega prime t, hopefully to make it shorter. So I'm taking the square of that. x0 square, c square, plus v0 square, omega prime square, s square, plus 2x0 v0 over omega prime sc. And kinetic energy is 1/2 mv square. This is 1/2 m. Now I will take the square of this term, e to the minus beta t. Let's take the square now, x0 square, omega prime square, s square, plus v0 square, c square, minus 2 omega prime x0 v0 sc. Okay, now we add them up. This is the total energy. Now this energy depends on time, and we shall find out how it depends on time. Let's look at these mixed terms, and let us also remember that k equals m omega 0 square, and we take omega 0 something like close to omega prime. So this is like m omega 0 square, x0 square, sine square. m omega 0 square x 0 square c square. So I have 1/2 k e to, I have an overall factor e to the minus beta t. Then this thing is 1/2 k x 0 square plus, let's look at that. I have m c square. This is m omega 0 square, omega 0 squares cancels that. So this is mv 0 square, sine square. Sine square plus c square is 1. So it is 1/2 m v 0 square. Hopefully they will cancel. x0 v0 over omega prime. This omega prime, this was m omega 0 square, so one of them cancels that. So these terms are canceling. When this is multiplied by m and when this is multiplied by k, which is m omega 0 square, and we don't at this moment differentiate between omega 0 and omega prime. Finished. But it's a beautiful result. This is the initial potential energy. This is the initial kinetic energy. So this is the total initial energy. So in this limit, in the limit of good oscillator, we obtained a very simple result, namely e to the minus beta t E0. So I will erase these things. Let me erase here. Let me write it here. E of t is equal to e to the minus beta t times E0. E0 is the initial total energy of the oscillator. We see that the oscillator is losing energy in an exponential fashion. So let me just draw here. This is the time t. Let me plot here E over E0, which is simply e to the minus beta t. So when t equals 0, it is 1. So it is exponentially decreasing. Okay, this is 1. So let us define a time td, damping time, which is 1 over beta. So when t is 1 over beta, we have e to the minus 1. So td essentially indicates the decay time. So td equals 1 over beta, we shall call it damping time. So after which we can basically forget about the oscillations of our oscillator. It's basically dead. Okay. Now, we have, now let me use the other way of representing the solution, namely the via complex phasor. So I am erasing it. We have learned this one, hopefully. Okay. Now I am back to solution again, because it will help us a lot in computing the kinetic energy averages of quantities, of physical quantities. Now, I want to represent the solution as the real part of x hat, and I want to write x hat as complex. It is a complex constant, e to the minus beta t over 2 times e to the I omega prime t. Remember, this omega prime square is the shifted frequency, minus beta square over 4. With x0 equals its magnitude times e to the I psi. So that, for example, the solution we can write as e to the minus beta t over 2 times x0 times cosine omega prime t plus psi. First, let us again find the I am erasing this energy argument. We have learned this for the good oscillator. Let me erase these. So the question is, this was A, remember, A, and this is B. What is the relation between x0 and psi, x0 magnitude? Psi. So if we simply open it up, the expression beta t over 2 x0 cosine psi cosine omega prime t minus x0 sine psi sine omega prime t. We see that x0 cosine psi is simply A, and x0 sine psi is equal to minus b, minus coming from here, minus b. From here, we solve x0 square, or rather this. If you square and add, this is up to 1. It is root a square plus b square, and tangent psi is minus b over a. So immediately make a connection between this solution and that. Okay. So again, let me just compute, for example, for this good oscillator, 1/2 k x0 square. What's that? Well, a square and b square are there. 1/2 k. So it is x0 square plus. So I'm considering for the good oscillator, I will neglect beta over omega prime. So it is k v0 square over omega prime square. So the first part, 1/2 k x0, is the initial kinetic energy, potential energy at time equals 0, plus k is m omega 0 square. So we can cancel omega 0 square, omega prime. So it is kinetic energy 0, 1/2 mv0 square. So it is simply the E0, or E at time equals 0. So you see, x0 square, this thing is related to total energy at the start of the time. Therefore, x0 is nothing but x0 is equal to basically x max. And show it that V0 is also V max. I give you that as an exercise. Let me erase this part. X equals e to the minus beta t over 2, x0 e to the I omega prime t, and V. Now, of course, you can take the whole derivative, but for a good oscillator, again, within a few cycles, this will not change. Namely, we are assuming Td, the damping time, is very much bigger than T prime, which is 2 pi over omega prime. So this is simply e to the minus beta t over 2, x0 I omega prime, e to the I omega prime t. So this is now B0. What have we done? We simply introduced the phasor representation, which is damped by this exponential factor due to friction. And so we can represent the solution like that. And we have seen that they carry the same meaning as in the ideal oscillator, except that in the ideal oscillator energy did not change. But here, of course, it is dropping with time with exponential e to the minus beta t. But now this is nice and important and very helpful. This is why we are doing it in introducing in computing the average values of physical quantities. So let me erase what I don't need here. I need this one. Now let me calculate the potential energy average. But let me remind you before I do it this beautiful relation. If you have two physical quantities, A physical and B physical, each varying with a time with a phasor e to the I omega t, then you can represent AP as the real part of A0 e to the I omega t. EP is a real part of B0 e to the I omega t. And this thing is 1/2 the real part of A0 B0, or 1/2 the real part of A0 B0. So it's a wonderful result where we can, if something is varying harmonically, we can take their complex conjugates and complex coefficients and compute the averages like this. Notice that you can use complex representation for the linear expressions. For example, in the equation, in the differential equation, we had only x. It was linear in x. So we could use complex representation and take its real part. You cannot use it in these are now bilinear, squared. You cannot use it there, except if it's varying harmonically, then only for the averages you can use it. Okay? And it's a wonderful result that you will see how it works simply. Sorry, I'm erasing this part again. I hope everyone memorized. So, what is harmonically varying is this. So, average is 1/2 k x squared. Remember, this is the physical, real x squared, time average. And of course, time average is over the t prime. And we assume t prime, that's our approximation of good oscillator. T prime is very shorter than the damping time Td. Okay? So that means we can take this time function as constant during the averaging interval. So it is 1/2 k, 1/2 the real part of. Now the coefficient of the harmonic function is this and that. So I have e to the minus beta t over 2, x0, and the complex conjugate of the other one. This is real, so it's the same thing again. So it is equal to 1/2 times 1/2 k e to the minus beta t. And I have x0 absolute square, which is real, so it goes out, x0 square. But we just computed in this good oscillator limit that this thing was E0, so it is 1/2 e to the minus beta t E0. Or if you wish, that's the E over 2, E of t divided by 2. Remember in the ideal oscillator, it was E0 over 2, and E0 was constant. But now, E is not equal to E0, E is E0 times e to the minus beta t. It is obvious that the kinetic energy is, again, E over 2. So, but however, let us compute. So it is 1/2 m the physical square over time. So it is, sorry, 1/2. So it is 1/2 m, 1/2 the real part of this thing absolute squared. So e to the minus beta t x0 square and omega prime square. So this is like omega, for a good oscillator, this is like omega 0 square, m omega 0 square is k x0, so it's the same result again. So it is E of t over 2. To summarize so far the energy argument, energy goes as E of t goes as E0 e to the minus beta t, and potential energy, kinetic energy average, is equal to potential energy average, and that's E, this E over 2, namely E0 over 2 e to the minus beta t. So it was if it were an ideal oscillator, beta would have been 0, E0 over 2. So it makes contact with the previous result. Okay, now there is an important concept with these oscillators. Now that our oscillators are not ideal, approximately how good an oscillator it is. So to measure that, traditionally one introduces a quality factor. I'm erasing this part. Okay. So as the name implies, quality factor tells me how good my oscillator is. Even though it is damped, how good is it? So it is defined like this. Quality factor Q equals, this is the energy stored in one period, in one cycle, divided by energy dissipated in 1 radian. Namely, this is the energy dissipated in 1 radian. So that's the historical why they didn't put here cycle, perhaps because of convenience that we shall see now. So this is E t prime, namely the average of energy. And this is 1 over 2 pi times energy dissipated in 1 cycle. And then this part we can write as follows. 2 pi goes up. This is 2 pi E average divided by. We can write the energy dissipated as the power dissipated times the length of the cycle. So it is T prime times the power dissipated in 1 cycle. So what is the power dissipated in one cycle? It's easy to compute. We have E equals E0 e to the minus beta t. And if you average E, that's E0 e to the minus beta t average, t prime. But we said within one cycle, remember we are dealing with a good oscillator. Within one cycle, e to the minus beta t factor does not change much, because at the beginning of the cycle, let's say it is minus beta t. At the end of the cycle, it is beta t plus t prime. And this factor, e to the minus beta t prime, is proportional to omega, 1 over omega prime, forgetting about the factor of 2 pi, and beta over omega prime is like 0. So this factor is approximately 1. So we can take this to be a constant. So it's again our old e to the minus beta t. Okay? Now, power dissipated will be minus, power dissipated average will be minus dE dt. But that's very easy to compute. It is simply minus minus cancels. It is beta times E. So let's put that in. Let me erase this. Quality factor Q is 2 pi over t prime E beta times E. So these cancelled. This is omega prime over beta. So you see why this 1 radian was introduced instead of the full cycle, so that you get this 2 pi here, and that 2 pi over t prime should give you omega prime. Okay. Now omega prime is root omega 0 square minus beta square over 4 over beta, which I can write as root, putting beta inside Q0 square minus 1 over 4. Q0 being defined as omega 0 over beta. So a good oscillator means Q is very large compared to 1 over 4. You know, if Q is 10, this is 100, this is 0.25. So to a good approximation, this is Q0. So this is the Q value of the oscillator. Again, if I am given an oscillator with these parameters K, M, and beta, so I know the answer. How good an oscillator do I have? What is my Q value? I will simply look at its Q value. It's omega prime over beta, or omega 0 over beta. Okay? So this gives me the Q factor. Now, in the good oscillator limit, namely weakly damped good oscillator limit, we can compute the correlation functions very easily and very quickly. I'm erasing all these. Let me write here again, for example, x equals e to the minus beta t over 2 x0 e to the I omega prime t. So for example, what is the average value of xt? This is the physical real quantity I'm writing, xt and xt plus delta. Okay? Over the period of one oscillation. So it is 1/2 the real part of, well, the coefficient is this, so I take minus beta t over 2 x0 times its complex conjugate. e to the minus beta t over 2 x0 star. But xt plus delta, in addition to the e to the I omega prime, has another exponential factor. So it is e to the minus I omega prime delta. Okay. So the result is immediate 1/2 e to the minus beta t x0 square, because x0 star is real, so we square, absolute square. And all we are left with the real part of e to the minus I omega prime delta. But this is cosine minus I sine of omega prime delta. So it is cosine omega prime delta. Now you recognize what this is. I multiply by k, divide by k. So 1/2 k x0 absolute square is the initial energy, E0. So it is E over k cosine omega prime delta, where E is E0 e to the minus beta t. Let's look at the velocity, v. That's e to the minus beta t over 2, x0 I omega prime, e to the I omega prime t. I'm differentiating this position. Again, since I will take the average in one cycle, during the cycle this doesn't change much. Doesn't change appreciably, remains, we can treat it as a constant. So v of t, this is the physical real v. V of t plus delta is 1/2 the real part of this thing, e to the minus beta t over 2 x0 I omega prime. Now the coefficient of the other one, complex conjugated, but the other one is evaluated at t plus delta, and it gives me another factor like that. So it is e to the minus beta t over 2 x0 star minus I, let me erase this, minus I omega prime times e to the minus I omega prime delta. So equals 1/2 e to the minus beta t x0 square omega prime square. I and minus I is +1, then the real part of e to the minus I omega prime delta. Now, if I multiply this by m and divide by m, m omega prime is like m omega 0 square k, and this is E0. So it is again E over m cosine omega prime delta. So you see, when we did the ideal oscillator, it was E0, because E remained constant, E0. Here, E is not remaining 0, so it is E0 e to the minus beta t cosine omega prime delta over m. That means it's the same thing as the ideal oscillator's correlation function, but multiplied by e to the minus beta t. I will not do it, but let me give you the third one. I can erase this part, perhaps. xt with t plus delta. All right, show that exercise. Show that this is minus 1/2 x max v max sine omega 0 delta, not cosine, sine, omega 0 delta, and times e to the minus beta t. Or, in short, we can write this in this way, all these results. Correlation functions for damped oscillator. But remember, we are talking about a good damped oscillator. Namely, a good oscillator is damped, but only slightly, okay? So this is equal to simply e to the minus beta t times correlation functions for ideal oscillator. Okay? This finishes our theoretical study of the damped oscillator, damped good oscillator, and in the next section I will solve some problems with the damped oscillator. We have not solved the mathematics of the differential equation. I will give that, you will find it in the homework problems. Thank you.